did really well. The one, I just want to remind you about the one that the most people lost a point or two on. Number 2. So you have a hanging pulley like this. And there's an 80 kilogram mass hanging from it. And then this one goes over to the wall. And these two angles are both 80. Rice.
Oh, you there?
Let's see.
Not in trouble, are you?
Go to the principal. Okay, so the way to do this is isolate all of the stuff that's hanging from the cable. So a free body diagram would look, you can imagine something like this. And actually, let me try to be a little more explicit about what I'm including here. Like, imagine that you are isolating So imagine you're isolating that mass and the thing that connects it to the pulley, and you're isolating in your system all of the cable that goes underneath the pulley. Okay, and so what forces are acting? There's a downward force of 784.8. And then the only other place the surroundings make contact is, now you can think of it as you're isolating some of that cable, and the cable that you're not including is pulling on the part that you are including. So you have two forces like this. But since they're not totally vertical, they're at an angle, you have to deal with those angles. This is a particle problem. We don't care about moments or anything like that. But so this is going to be t times the cosine and sine of 100 degrees. That's for the one on the left. And then plus t times the cosine and sine of 80 degrees. And then plus 0, negative 784.8 is equal to zeros. And you can see that this should have been 100. Oh, no, it isn't. This is 80. Okay, well, cosine of 100 and cosine of 80, that gives you, you can think of this as two equations. The first one says negative 0.174t plus 0.174t is equal to 0. Those cancel out, so that one doesn't help you. And then the second equation says 0.985t plus 0.985t is equal to 784.8. And then so T is equal to whatever it's equal to, about 800.
It's 398.
Yeah. So T is equal to 398 newtons. And then from there, you can go and for part, so this is the answer to part A. For part B, you're trying to figure out, so you know that this angle is 80 degrees. Now you know that the magnitude of this force is 398. And so that's just figuring out vector components. And then for C, it's the same thing, but the cable is pointing this way, where this angle is 30 degrees. Anybody have any questions about that? Tell me your name again.
I'm Elizabeth. Thank you.
Yeah, for some reason I thought that whenever you have the same degree angle,
Mm-hmm.
no matter what, it's just gonna cancel out.
Yeah. Uh-huh.
So it's always gonna be.
Yeah. If you go, if you set it up like this, so
So I know if it says like 160, 180, then it's gonna be. different.
so if you set it up like this, and then where say that angle is, 2 degrees or something, this force is going to get way bigger than the weight force of that thing. And as that cable gets closer to horizontal, the tension in the cable approaches infinity. So you got to do it with the cosine and sine on that. Okay? Anybody have any questions about the test? A couple people did the extra credit and did it all right, so that was great. That was a lot of work for 1 point, though. Okay, so what we were doing last time, we're starting talking about structures. And we're in the middle of a problem. Where we have this equilateral triangle. And all of the joints are pin joints, so that's a pin joint up there. And all of the lengths are 1 meter. And the masses of these two members are 20 kilograms. So what we're trying to do is calculate the external loads on each one of these members. And we're going to break this thing up into the following pieces. What we're calling member 1 is this thing over here, and it has cutouts at the 2 pins. So those aren't part of this. That's member 1. And then the pin here is A. The pin here is B. And we're treating those like particles. We're ignoring the dimensions in this plane. And then we have another member here, member 2. And then we have C. And we did rigid body statics on each of the 2 long members, 1 and 2. And that gave us the following set of equations. We have F, the force on body 1 by the pin A. This isn't a vector. This is an X component. Plus the force on body 1 by the pin B, X component, is equal to 0. The second equation, F on 1 by A, Y, plus F on 1 by B, Y, is equal to 196.2. And then the moment equation from this one said negative 0.5 F1BX plus 0.866 times the force on 1 by B, Y component, is equal to 84.95. So that's from body 1. And then from body 2, we have 3 more equations. The force on 2 by the pin B, X component, plus F2CX is equal to 0. Now the same thing with the Y components, F2BY plus F2CY is equal to 196.2. And then the 6th equation says 0.5 F2CX plus 0.866 F2CY is equal to 84.95. Okay, so that's our 6 equations so far. And how many variables do we have? That's a rhetorical question. Keep quiet. This is my show. Okay, so we got the force on 1 by A, X and Y components. The force on 1 by B, X and Y components. The force on 2 by B, X and Y components, and the force on 2 by C, X and Y. So yeah, 8, you were right. Okay, so 8 variables with 6 equations. So we can't solve it yet. Okay, yes?
Would you be able to solve it just by making isometry the ones that are equal? Like some of the components of Y are going to be equal and some of the components of X are going to be equal but opposite.
Could you do it with symmetry? Well, you know that the force on... Yeah, I mean, basically that is what we're going to do is we're going to enforce that symmetry, but we're going to do it through Newton's second law. by treating each of the pins as a particle. Okay. All right, so we know we need 2 more equations. So let's look at, okay, so we need 2 more equations without introducing any new variables. Well, what's going to happen if we isolate that pin at A? What forces are going to act on that? There's going to be a force on A by member 1. That's okay. We can use Newton's third law to make that a variable we already have. But there's also going to be a force on A by the ground, okay? And that's a new variable. So let's see if there's a better thing we can do. Let's go up and look at B. Okay, and if we isolate the pin B, what forces act on this? There's a force on B by body 1, which Newton's third law says is negative force on 1 by B. And there's also a force on B by member 2, and Newton's third law says that's equal to negative force on 2 by B. And those are all the forces on that. We're assuming this has no mass relative to the others. We could put that stuff in, but assuming that this mass is pretty tiny compared to those other things, it's not really going to affect the answer. Okay, so what does this say? So Newton's second law says we have a 7th equation, negative F1bx minus F2bx is equal to 0. And you can see that's the symmetry. And then 8 says negative F1by minus F2by is equal to 0. And now we have this system, 8 equations for 8 variables. Well, let's solve this. We need 8 rows and 9 columns. One, two, three, 4, 5, 6, 7, 8, 9. And okay, so this row is equation 1, 2, 3, 4, 5, 6, 7, 8. And then we have the force on 1 by A, X and Y. The force on 1 by B, X and Y. The force on 2 by B, X and Y. And the force on 2 by C, X and Y. And then the constant. Oh, yes?
I was wondering, could you go back and substitute so we'd have less equations?
Yeah, you could do that.
Okay.
For sure, yes. Anything you spot that can reduce the number of variables and number of equations, as long as you reduce them in the same number, you can do it. So, okay, what does this first one look like? F1AX has a 1, F1BX has a 1, everything else is zeros. Then F1AY and F1BY have 1s, and the constant is 196.2. Then the third equation, F1BX has a negative 0.5. F1BY has a 0.866. And the constant is 84.95.
Did you mean to put it in the rungs column for negative 0.5?
Negative 0.5.
It should be bx, right? Not ax.
1bx, thank you. I did not mean to do that. Equation 4, F2bx has a 1. F2cx has a 1. And constant is 0. And then the y variables have 1s, and the constant is 196.2. And then 2cx has a 0.5. Positive 0.866 for 2cy, and then the constant is 84.95. And then negative 1 for 1bx and 2bx. And zeros everywhere, and then the same thing for the y's. Okay, let's pause this. And what I got is the force on 1 by A is equal to 169.9, 196.2. Oh, yay. F1B is negative 169.90. F2B is positive 169.90. And F2C is negative 169.9, 196.2. Okay, so what this says is you have a force vector down here on this member of, well, let me draw the directions too. So we have a force this way of 169.9 and an upward force of 196.2. A weight force of 196.2. And a force in the negative x direction of 169.9. And then on the other member, we have the weight force of 196.2. We have a horizontal force this way of 169.9, an upward force of 196.2. And then at B, we have a force in the negative x direction of 169.9. Okay, so there's the complete free body diagram. Okay, well, we can simplify that a little bit, but this is all based on stuff that we already knew how to do. So now I'm just going to give you like a set of steps that you can use that'll kind of minimize the number of variables and equations. What we are going to do, so we can simplify this a little bit. And still keep this method completely general, like it'll still solve any structures problem that has a solution just based on statics. So we can still be able to solve any statically determinate structure. There are some structures you can't solve just with the statics, and there's nothing you can do about that. By the way, like, what would it look like to have a statically indeterminate structure, a structure you can't solve just by statics? So this is the minimum number of joint constraints that you can have and still have this thing be static. If you took away, say you took one of the two joints on the floor, if you took away the ability of one of those to produce a horizontal force, this thing would not stay at rest, okay? So if this is absolutely constrained as little as you can and still solve this with statics. If you add any more joint constraints, then there are multiple possible answers for this. Infinitely many, actually. So if we took another bar and went from here to here, there's nothing wrong with doing it. It would make this structure a little stronger. But you would need other approaches in order to solve the reactions at this point. That's statically indeterminate. And you'd have to use methods from deform that we'll learn in deform to solve this. Okay, so erase this. Okay, we're coming up with a general method that sort of optimizes this. So here's a general optimized method. First, number all the members. And give letter names to all the joints. And what I am going to do is, instead of treating the pins as individual bodies, particles, and then using Newton's laws on those, I'm always going to choose for the pin to be, I mean, you know, you can group multiple things into a single body. There's no problem with that, you know. If you do a free body diagram of a person, you're doing a free body diagram that includes a billion different cells and all this stuff, right? You can lump multiple things in. So we're going to lump the pin, each pin is going to be lumped in with one of those bodies, okay? And how are we going to choose which body? Because it's sort of a bookkeeping problem. We have to keep that straight. Otherwise, you'll end up double counting forces and stuff. Include each pin in the lowest numbered member that touches that joint. Okay, what is it about the lowest numbered member? There's nothing about it. It's just a bookkeeping thing, you know, but that's just what I'm going to do. So it'd be easier for all of us if you did the same thing that I did. So what does that mean in these individual cases? So if we call the one on the left member 1 and the one on the right member 2, we're going to lump, well, the pin at the ground on the left touches member 1. It also touches the ground, or the bracket in this case. We didn't even number the bracket, so we'll just sort of by default, we'll say that's part of member 1. Okay? Then the pin at B at the top, what does that touch? There are 2 members that touch it, member 1 and member 2. 1 is the lowest numbered member there, so we'll include that also in member 1. Then finally, the one at C, that connects the bracket, the ground, with the member 2. 2 is the lowest numbered member. It's the only numbered member. And so we'll lump that pin in with member 2. Okay, so let's do that. So let's do this again. And I'm going to call this member 1, this member 2, A, B, and C. I'm just doing the same problem again. And to visualize this, let's think of a side view of each of these pin connections. Okay, sort of an idealized side view. You wouldn't want to make a joint that actually looked like this, but this is how we're going to think of it. So at joint A, there is the bracket, and there is member 1. And those 2 are connected by a pin, but they don't touch each other. Okay? Can you visualize that? Okay, so what's member 1? Member 1, we're lumping the pin in with it. It's the lowest numbered member at that joint. So all of this now is considered member 1. Okay? And now let's go to joint B. Side view. So here's member 1. Here's member 2. They're angled opposite directions. If you can sort of visualize that, we're looking from the side. And they're connected by a pin. Well, 1 is the lowest numbered member at this joint, and so the pin is considered to be part of member 1. So the red is all member 1. Okay? And then the last one looks like joint A. We have the ground, we have that bracket, and we have member 2. And the only thing that touches both of them is the pin. The lowest numbered member there is member 2, so the pin is part of member 2. Okay. Anybody have any questions about what I'm talking about here? So now we're not considering any pins. We have a system for what body each pin is a part of. Okay. Okay, next. So that was step 1. Step 2, for each member, do a rigid body static analysis. And this is a key step for being able to solve this. You're going to, like when you go from one body to another body, there are going to be times where you're going to get a force that has the opposite subscripts of what you just did, okay? Use Newton's third law on that to reduce the number of variables. So reduce the variables using Newton's third law. And Newton's third law says that the force on, say, A by B is equal to negative force on B by A. Okay? And then the last step is augmented matrix, and then reduce row echelon form. If you've done this for every body, for each member, let's say, and you have more variables than you have equations, that means that the problem's statically indeterminate, or you mess something up, actually more likely. But if you do it and you have too many variables and then you do it again and you get the same thing, then you start to be a little more confident that this just isn't solvable. Okay, so let's do a problem, and I'm going to do a pretty similar one. Well, okay, so let's say that we have a new thing. There's a pin there, and a member like that. And then what am I going to do here? A pin there and a member like that. And let's say that this is a 3, 4, 5 triangle. So I'll call this 1 meter, 0.8 meters, and 0.6 meters. And let's apply an external force here of 1,000 newtons. And we'll neglect the masses this time. Okay, and let's just think through the steps. So first, I'll call this member 1, this member 2. There's A, B, and C. And now I'll do a free body diagram of member 1. There's a force over here that I'll call the reaction force RA. This is the only one I'm not going to use that subscript notation for because it's connected to the ground. The subscript notation is only helpful if you're going to consider the other body at some point. Okay, so for the things that are in contact with the ground, we'll just, give it some random reaction force name or whatever. Okay, at the other joint at B, the two joints that are the two members that are touching the pin are member 1 and member 2. 1 is the lowest numbered member. Okay, so I'm going to consider the pin to be part of member 1. Okay, and that means that I'm going to apply that 1,000 Newton force to member 1 because it's acting on the pin. Okay, so over here, I have the downward force of 1,000. And then what's the force vector that acts at that point? Well, so what external object is in contact with member 1?
Should be 2.
Yeah, 2 is in contact with the pin, and the pin is part of member 1. So we can call this the force on 1 by 2. Okay. And then you can write out a table. This one, it's probably easiest, fastest just to use, since this is basically like a horizontal beam, I'm just going to sort of think through it. So Newton's second law, our first equation says RAX plus F12X is equal to 0. The second one says RAY plus F12Y minus 1,000 is equal to 0. So this is equal to 1,000. And then the third one is the moment equation. RA doesn't produce any moment. Okay, and then there's a moment arm of 0.8 on this downward force of 1,000. With this red about point, would that 1,000 Newton force make this body rotate clockwise or counterclockwise? Clockwise, so that's negative. And then the horizontal component of F12 isn't going to produce a moment because its line of action goes right through the about point. But the vertical one is. So we have plus or minus, again, a moment arm of 0.8 times F12Y and this is equal to 0. The F12y, its default direction is up. So would an upward force make this rotate clockwise or counterclockwise? Counterclockwise, so this is positive. And so you can rewrite this equation as 0.8 F12y is equal to positive 800. So we have these two first equations. This is the third equation. And then we go on to body 2, and we're out of time. If you have time this weekend, see if you can think through the rest of this and get an answer for this. And then I'll finish this on Monday. But so now we're going on to body 2. All right. Notice that since we're always just doing a rigid body analysis for all the members, the number of equations that you're going to get from any structure is just going to be 3 times the number of bodies you have. Okay? So when we did that sort of full first form of a problem like this, we had a system of 8 equations for 8 variables. Now we've managed to cut this down to a system of 6 equations for 6 variables. Everything helps a little, you know. Okay, that's all.